that require us to find maximum or minimum points in that situation. I've kind of sketched an example here on the board of that might illustrate this. Let's say you work in a manufacturing facility and you're looking at the graph of the cost per unit to produce whatever it is. Maybe it's graphing calculators. And the cost per unit to produce graphing calculators starts out fairly high because you have to lease the facility and turn the heat on and turn the lights on. But as you are able to produce more than 0 units, or you increase the number of units that you produce, the cost per unit comes down because you get to absorb that cost of heat and lights and lease over many units that you're going to produce. So that cost per unit comes down. At some point, and this axis represents the number of units produced, at some point you might get into a situation where your facility has outgrown itself, at least on a shift. So maybe what you have to do is you have to add a second shift, or maybe you have to work overtime. But what happens then is that you have to pay either time and a half, or maybe you have to pay double time because you're working people overtime, and your cost per unit might go back up a little bit again. Or maybe you even have to rent a new facility, so your cost per unit is on the rise again. This is a situation where I would like to know a minimum point. I would like to know the cost per unit that is a minimum and how many units I would produce in that circumstance. That allows the manufacturer to decide what their profit and revenue will be, because they'll probably operate right here, or they'll think about operating right there when their cost per unit is at its lowest. Read with me now problem number 4 in section 7 of this chapter that involves quadratic equations. The problem reads, a stonemason has enough stones to enclose a rectangular patio with 60 foot of perimeter. Assuming that the attached house forms one side of the rectangle, what is the maximum area that the mason can enclose? What should the dimensions of the patio be in order to yield this area? So you should read that problem a few times, but I've shown the patio here, and I want to allow the perimeter that's enclosed by stones anyway to be 60 feet, and I want to choose to get a maximum area out of using those 60 feet of stones. So what you have to remember is you have to remember these two equations are going to come into play. The perimeter of a rectangle is twice the length plus twice the width, and an area of a rectangle is length times width. But in this particular case, if I let this be L and this be W, I'm not going to use L twice because the house is going to be the binding wall, the fourth binding wall. So if I have 60 foot of stone, I'm going to use this equation. If I have 60 feet of stone, then I'm going to have 60 equals L plus 2W, not 2L plus 2W, just L plus 2W. And then next I have this equation, area equals length times width. And I want to maximize that. So what I'm going to do is I'm going to take this equation, and it doesn't matter which variable I solve for, but it's much easier to solve this equation for L. So I'm going to rearrange it, and I'm going to say that L equals 60 minus 2W. So I'm going to move this over to the other side. And then I'm going to replace that statement into this piece in the equation right here. So I'll have A equals 60 minus 2W is going in for L times W. And then next, I'm going to distribute this W times each of the terms here. So W times a minus 2W is a minus 2W squared, and W times 60 is a positive 60W. And what I'm going to do is I'm going to maximize this. I'm going to write this problem so I can find the maximum point. So I'm going to complete the square again, and I'm going to give a sketch for you. To complete the square, I have to factor out a minus 2 because I have to have the first term, oops, excuse me, I have to have the first term be a 1W squared. I'm going to need a minus 30, got to be careful here, W there. Just going to check back in, step back and check that. Yeah, that looks good. To complete the square, I'm going to take half of this minus 30. I'm going to do this over here. Half of the minus 30 and square it. So I'm going to be taking a negative 15 and squaring it, and so that's 225. So I'm going to take W squared minus 30W, and I'm going to add 225, and I'm going to subtract 225. Please remember to add and subtract it so that you have added 0. All right. Next, I'm going to take the first 3 terms and write that as a binomial squared. That's going to be a W minus 15, that quantity squared. I'm going to copy everything else. Oops, I'm going to be careful. Hang on a minute. I just want to check that it's supposed to be a minus 15. This minus 2 has to be multiplied by this minus 225 to give me a positive 450 at the end. And this equation is now in the form of a times x minus h, that quantity squared, plus the constant k. So I can find that my vertex, and I'm going to jot these down over here, my vertex is where x is a positive 15 and y is 450. My line of symmetry, and again, this is not everything that I didn't need to do all this, is where x equals 15. And because I have a negative 2 here, and here is where I'm going to put a sketch of this, because I have a negative 2, this is actually going to be way up here, way up here. It's going to look something like this. I have a curve that's opening downward, and so I have a maximum, not a minimum, and my maximum is at 450. Now remember, 450 represents my y value. That's going to be my area of this patio. So I'm going to get a maximum area of 450 square feet. I believe these units were in feet. And x represents my width, if you will, here. And so my width turns out to be 15 feet. 15 feet is my width. My length, therefore, from this statement right here, if twice 15 is 30, and I subtract it, then my length will be 30 feet. And my maximum area will equal 450 square feet. And you can check that by just taking those two numbers right there, 15 times 30, and multiplying those together. Kind of a challenging problem, maximum and minimum problems. I'll ask you to do that once on our test. It involves writing two equations and taking one of the two equations, solving for a variable and substituting into the other, and getting a quadratic equation. And then graphing it and looking for that maximum or that minimum. Number 10 in section 7 is also actually this is a minimizing problem, and it reads like this. Again, number 10. It's about stock prices. The value of a share of RP Mugatti in dollars can be represented by V of x equals x squared minus 6x plus 13, right here, where x is the number of months after January 2003. What is the lowest value V of x will reach, and when did that occur? Again, x is when, V of x is that value. So we're looking for our vertex and our minimum in this problem. So it really is just a completing the square problem. So I'm going to take this x squared minus 6x. I'm going to divide the minus 6 by 2, and then I'm going to square it. So I'm taking that b value, cutting it in half, squaring it. That's a negative 3 squared, which is 9. So I'm going to add 9, and I'm going to subtract 9, and then I'm going to bring down that positive 13. Next, I'll take the perfect square trinomial, which is always in the front, and I'll factor that into the product of two binomials, or that binomial squared. Remember, the minus 3 is what goes in this spot. Then the negative 9 and the positive 13 add to be a positive 4. I'm done. My vertex in this problem, if I were to graph it, is the x value will be a positive 3. My y value will be a positive 4. It says that 3 months later, after I believe that was January 2003, that the stock price will be $4. My line of symmetry, again, if I were to graph this, is where x equals 3. That's the minimum point. Yes, this is a minimum, because I'm looking at a graph that looks like, and I'm going to try to sketch this. Here's my vertex, and it's going to look like that to some degree. And so now I would say that my minimum is $4. 3 months, again this point right here, 3 months after January 2003. The very last thing that I'm going to tackle in this chapter is to be able to write a quadratic equation from data, to be able to model it, basically. There is a calculator corner in the very end of this section that describes how you would do this by letting the calculator do all the work. It's called the regression feature on the calculator, and you use the stat key to do that. I am asking you to do that with a project in that calculator corner, to use the problems right in that calculator corner. It's tough for me to show the calculator on the with this video camera that I'm using, so I'm not going to be able to do that. Again, those calculator corners are fairly self-explanatory in that you follow them exactly, hit the buttons exactly as they say so. What we're going to do here is we're going to do this by hand. We're going to model a problem by hand. So here's what you got to do. I want to write a quadratic function to fit data, and here's my data. 3 data points. X is 1, Y is 4, X is a negative 1, Y is 6, X is a negative 2, Y is 16. And I have attempted to put this data on this graph with this ordered pair being way up here, coming down through here, and then I don't know where it goes at this point. So here's my ordered pair, and I'm going to attempt to write a quadratic equation that goes through those points. I have to have 3 points in order to write a quadratic equation. I cannot do it with 2. 2 points make a straight line. 3 points will help me to build the curve. What you now have to remember is you have to remember the standard form of a quadratic equation. And with these ordered pairs, one at a time, you have to put them in here. Again, recognize please that this is my y value in this ordered pair, so I'm going to put it in for y right here. And then my x value in this ordered pair is 1, so I'm going to put in a 1 right here for x and square it. My x value again is 1, so I'm putting it in for x, and then I have my constant c. So I'm going to clean this equation up. What I have is 4 equals, that right there is a 1a, this is a 1b, and a 1c. And I have a linear equation in 3 variables. I'm going to do this again with both of these. So now I'm going to go into this form of the quadratic equation, and I'm going to put in for y a value of 6 because of that value right there. And then for x, I'm going to put in a negative 1, but I want to square it. And then I'm going to multiply b by that x value, which is a negative 1, plus the constant. And let's clean this up now. A negative 1 squared is a positive 1, so I have a 1a, and then a minus 1b, and a plus c, and I now have a second equation in 3 variables. I can't solve linear equations in multiple variables until I have an equal number of equations. So I have 2 equations right now with 3 unknowns, so I've got to create a third equation. So for y, I'm going to substitute in a 16. For x, I'm going to substitute in a negative 2. I've got to square that. Plus b times x, which is a negative 2, plus the constant c. And I now have a negative 2 squared is 4, so I have 4a. A negative 2 times b is a minus 2b, plus the constant c, and I now have my third equation. I'm going to stop the camera for a minute, and I'm going to copy these 3 equations down on the board, and we're going to solve those 3 equations as a system of equations. I've never done a video on this topic, and this is probably a good one right before the final exam time to do a problem like this where there's 3 equations and 3 unknowns. So I'm going to stop and I'm going to put those back up and we'll complete this problem. We're ready now to solve this system of equations, 3 equations and 3 unknowns. I'm going to choose to eliminate the variable b. Remember, that's what you must do to solve a system of equations. You have to choose to take the 3 equations and whittle them on down to 2 equations with 2 unknowns by eliminating a variable twice. I'm choosing to eliminate the letter b because these 2 equations right here, when I add them together, eliminate the b right away. So I'm going to add the first and second statements. 4 and 6 is 10, 1a and 1a is 2a, b and a minus b adds to be nothing, and c adds to be 2c. When I teach this in the classroom, I like to star or mark those equations, that linear equation in 2 variables, because I'm going to use that again in a minute. Now that I've used these 2 equations, I need to either use these 2 equations and get rid of the b, or these 2 equations and get rid of the b. I think I'm going to go ahead and just multiply this equation right here by a negative 2. So I'm going to multiply this by a negative 2. What that will do, that will make this become a positive 2b. And then when I add it to the third equation, I'm all set. So 6 times a negative 2 is a negative 12. This will become a minus 2a. Negative 1 times a negative 2 is a positive 2b. And this will be a minus 2c. And then I'm just going to copy the third statement. And that's going to be the 16, the 4a, minus the 2b, and the plus c. And I'm ready to add those. So this adds to be 4, this adds to be 2a, that adds to be nothing, and this adds to be a minus 1c. And I have my second equation with two variables in it, both of those being a and c. I'm going to start again. No, actually, I'm going to go over here, I think, and work this. So I'm going to get rid of these notes to myself, and I'm going to take the 10 equals 2a plus 2c and copy it, and then this 4, which equals 2a minus c, and copy that. And now I want to solve that system of two equations and two unknowns. And you know, to save myself a little bit of space, I see that these a terms have the same coefficient, and I want to add them. I like to use what's called the addition or elimination method. So I'm going to add the opposites. I'm going to multiply this whole equation by a negative 1. So I'm going to make that a minus 4. I'm going to make that a negative 2, and I'm going to make that a positive c. I can do that because I've multiplied both sides by a negative 1. I'll add this, and I'll have 6 equals, this adds to be nothing, 2c and 1c adds to be 3c, and now I can divide both sides by 3, and I can find out that the constant c is equal to 2. I think I'll jot some of those values down here. C is 2. I want to find out what b is, and I want to find out what a is. If c is 2, I can go back into one of these two equations and find out what a is. I prefer actually this equation, which without the signs. So 4 equals 2a minus c, and c is 2. So let's add 2 to both sides. I'm not going to show the work. That'll give me a 6 on the left. Then I'll divide both sides by 2, and I find out that a is equal to 3. Last but not least, I take those two values, put them into one of these three equations. I like putting it into this top equation because if a is 3 and c is 2, those two add to be 5. Let's subtract 5 from both sides to get b alone, and 4 minus 5 is a negative 1 for b. Finally, I'm ready to put those values into this equation because after all, that is in fact where I started. Ax squared plus bx plus c, to model this data. And so what I know then is that data has a quadratic equation that fits through those 3 points, that a is 3, so I have a 3x squared, b is a minus 1, so I have a minus 1x, c is a positive 2, a positive 2. This is the quadratic equation that goes through those ordered pairs. And in fact, I was sitting and looking at this thinking, oh, I don't see how that's going to work. It's hard to draw, but it actually does something like this. It goes down like that, and these pairs are a little bit askew, if you will, and it goes like that. So that's what I really have, and I know that because I went ahead and completed the square on this, but I do know that this crosses the y-axis at that point right there, and that's what gave me my tip. I knew that this picture wasn't valid, as I had originally just sketched it. You've now got a Chapter 7 test to face, and it's a proctor test. You need to take it at your local testing center. You're going to be given a couple hours. You're going to take your graphing calculator in to do that. It will be given to you in order, again, in order that you've studied the material. So, for example, I'm going to ask you to solve quadratic equations at first. And I'm only one time going to say to you that you must solve it this way. And that is one time I'm going to ask you to solve a quadratic equation by completing the square. Otherwise, it's up to you, the method that you choose. You can solve by factoring if the problem's factorable. You can solve by graphing it with your graphing calculator and seeing where it crosses the x-axis. The dilemma with this is that I'm going to be asking for exact solutions. And when you solve it by graphing, you get a decimal value, which rounds off to some point. The quadratic formula will always give you an exact value, and you have to be careful with simplifying that. Some of the other things that we addressed in this area, in the first 4 sections, was finding the nature of your solution. And all we cared about there was what the value of the discriminant was. That's the value underneath the radical in the quadratic formula. If the value underneath the radical is positive, we said that there are 2 solutions and they're both real numbers. If the value underneath the radical was 0, we said that there's only one solution to that quadratic equation. It just touches the x-axis and it's a real number. If the value underneath the radical was a negative number, we said that there are 2 solutions, but they're complex numbers. They involve an imaginary value, so it's an imaginary root. If you tried to graph those wouldn't cross the x-axis at all. We also learned in the first 4 sections, on top of how to solve a quadratic equation, we learned how to, given 2 solutions, write the equation that would fit that. So we said to you, if x equals 3 and if x equals 3 and x equals 4, write the quadratic equation that would have those 2 solutions. Then we went into graphing the quadratic equations, and we started very simply with just an x squared term. Then we went into a position where we wrote it as a binomial squared, x minus h, that quantity squared, and we found the vertex and the line of symmetry. And then we added a constant to that and a coefficient in front of the binomial, and we had to find maximum or minimum points. So we spent a lot of time with graphing. And finally we went into that last section where we did some work a little bit with story problems and finding maximum and minimums, and we learned how to model an equation given some data. I would highly suggest, and this is a major suggestion, that you take a look at the test in the book. It's easier than the online test, although that shouldn't be too bad for this chapter. And I do require and ask you to take the practice test online. But there's a practice test in the book at the end of the chapter. That's a great thing to practice, to get ready, because it does everything that we've done in this chapter. The review is good too in the book. It's just a little bit longer. Practice test won't take you quite as long. Good luck. Make sure you keep on top of things. Don't wait until the last minute to take this test, because that just means that your final exam is going to be taken at the last minute. And final exam closing dates are very close to the Christmas holiday. It can get to be really stressful, so please try to get at this as soon as possible.